We are going to use the potentiometer today to find the internal resistance of a primary cell. You know that a primary cell has electrolyte and the ions in them cause the potential difference to be created. So, there is a positive and a negative terminal. The electrolyte offers the internal resistance and you can check that out and find it accurately using a potentiometer. So, in order to do this experiment, let us see the apparatus we need. We require a battery eliminator, a rheostat, a key to allow the current to flow through this and thereby set a potential difference across here. This is our Leclanche cell. You can see the electrolyte ammonium chloride in it, the zinc rod forming the negative terminal and the carbon rod at the center forming the positive. If you remember, your equation was E is equal to V plus I R, where V is the terminal potential difference for this particular cell, I is the current flowing in this circuit and R is the internal resistance. We want the internal resistance of this cell. So, the positive of this cell is to be connected to our positive point on the potentiometer, which we have labeled as positive here. The negative, which is our zinc rod, is connected to the galvanometer. The galvanometer to this jockey. The circuit in which we are going to draw current from this Leclanche cell is connected across these two. So, from the positive terminal I have this resistance box, the key connected to the galvanometer and the jockey. The choice of choosing this circuit to draw any current from the Leclanche cell is going to be done by this key, the key in this circuit. The main key is for current in the potentiometer wire. So, let us see what readings we are going to take. We will first, without this second circuit being connected, we will find a position on the potentiometer wire where there is no deflection in the galvanometer. After that, we will take out some resistance from here, allow the circuit with the cell to work. Therefore, its potential difference we are expecting to drop and become less than the e.m.f. So, we will again look for a position of null point on this particular wire. To take more readings, we can choose small values of resistance across it, say 2, 3, 4, 5 ohms, and put it in our observation table. Let us see what we will fill in our observation table. After starting our switch from the eliminator, connecting up the key in the main circuit, this key is off. We will start by using the jockey. First, on the first wire, this is giving me left side deflection. On the last wire, it is giving me right side deflection. That means the circuit is correct. The e.m.f. provided by the main eliminator here is greater than the e.m.f. of the Leclanche cell, and you can get a null point on it. So, let us look for our length which will give us a null point with just the cell. That means between these two wires, somewhere here is our null point. Carefully note this value of L1, where there is 0 deflection in the galvanometer. This length is 254. So, you can check this value from here. At the beginning of the experiment, this balance length L1 is 254 centimeters. Now, we will use the second circuit by putting the key to draw current from this Leclanche cell in this circuit. From here I have taken out 3 ohms and I need to record that in my observation table. Balance length L2 is what I am going to look for now, because now the cell is in use, the terminal voltage is going to give me the balance length. Let us check the circuit again. Why do we have to do that? Because should the potential difference have changed anywhere for any reason, you would be knowing that the circuit is working correctly or not. It normally should, because now the potential difference across this is lower. However, deflection on the right, deflection again on the right, suggesting have we lost the null point? Let us make this length lesser and see the circuit is correct. That means the internal resistance is causing the potential difference across the terminals of this Leclanché cell to be even lower than what you are expecting. So, watch, you look for the balance length and this balance length is obtained here, 0 deflection, and this length I will need to record as L2 and it is on the first wire. So, its value is only 26.5. So, the balance length L2 is 26.5 for a resistance of 3 ohms. I can make that value 2 ohms and check out the balance position again. Somewhere here is my null point. Make note of the length again on the first wire, and this length is only 18 centimeters. Take for 4 ohms. Look for the null point. On the first wire, 34 centimeters. You can take more readings like this, at least 5 you should have, and for each of them you are going to use the formula. The resistance of this cell is equal to L1 minus L2 upon L2 multiplied by R. This R value for each reading will be the one that you have taken out from the resistance box. So, you will get a set of values for internal resistance. You can find the mean of that. You can also plot a graph relating 1 upon R and L1 upon L2. The slope of that line comes out to be the reciprocal of the internal resistance. You can work that out and do it as a project. Do more experiments with different cells, finding out their internal resistances, finding out what happens when you change the concentration of the electrolyte. Make up a cell in which you can increase the distance between the positive and the negative electrode. That will tell you that the internal resistance depends on that factor. You can change the concentration of the electrolyte and study what happens to the internal resistance. A lot of experiments can be done by using this particular apparatus and the same circuit. So, you have learned today how to find the internal resistance of a primary cell. In this case, we had selected the Leclanché cell. You could do the same for a simple voltaic cell or for a Daniell cell. You have also learned how the potentiometer gives you a very accurate way of finding the value for internal resistance, the e.m.f, the terminal voltage.